Hey everyone, and welcome to This Explainer. Today we're going on a bit of a mission. I want you to imagine you're a network engineer, and you've just unboxed a brand new, wildly expensive enterprise Cisco router. Your mission? You've got to configure it, troubleshoot it, and get it fully online so it can flawlessly navigate the incredibly complex map of the internet. If you've ever found yourself wondering what actually happens behind the scenes to keep our entire digital world connected, well, you're definitely in the right place.
But before we even think about plugging anything in, I really want you to ponder this for a second. When you hit send on an email, how does a single tiny packet of data actually know where to go? It kind of seems like magic, right? Well, the truth is, the so-called magic of internet routing is honestly just like a massive postal service sorting facility. Every piece of data needs a unique address, a designated sorting machine, and a super clear path to its final destination. Without those three things, your data is literally just lost in the void. So let's see how we build that exact infrastructure totally from the ground up.
All right, let's kick things off with phase one, booting the Cisco router. Okay, so here's a wild reality check. Right out of the box, your incredibly powerful top-of-the-line Cisco router is essentially just a blank slate. It has absolutely no idea where it is, and it definitely doesn't know where to send a single byte of data. Let's ground this in reality for a moment. Before any of the command line magic can happen, you've got to physically rack and cable the device in a data center. You're plugging in the Ethernet cables, your serial WAN links, and physically powering it up. You are the one physically building the literal on-ramps and off-ramps for your data.
Now, once you're all plugged in and you've logged into the console, you hit your very first hurdle. Cisco router interfaces actually default to a completely disabled or shutdown state. You might be wondering, why on earth do they do that? Well, it's actually a built-in security and stability feature so you don't accidentally bring down an entire network with one misconfigured port. So what do? You jump into the command line interface and literally type the no shutdown command just to wake the thing up. Until you do that and give it an IP address, your router is completely deaf and blind to the world around it.
Moving right along, we arrive at phase two, building the routing table.
Okay, let's dive into this. The router is finally awake, but now it has a major problem. It needs a map. It needs to know exactly how to act as that postal sorting facility we talked about. And here's the crazy part. Every single time a data frame arrives, the router executes this strict 5-step dance. Step 1, it receives the data link frame right off the wire. Step 2, it de-encapsulates it, literally stripping away the outer shell to reveal the IP packet hiding inside. Step 3, it looks at that destination IP address and checks it against its routing table map. Step 4, it encapsulates that packet into a brand new frame, getting it ready for the next leg of its journey. And Step 5, it transmits it out the correct physical interface. Every single packet, millions of times a second, goes through this exact logic sequence.
So you're probably asking, how does the router actually get that map in the first place? Well, first off, the router does have a built-in sense of its immediate surroundings. We call these connected routes. Basically, as long as an interface is active, awake, and has an IP address, the router automatically knows about that specific local subnet. It's kind of like knowing the layout of the rooms in your own house. But for everything else out there in the big wide world, we have to draw the MAC entirely by hand using static routes. You, the engineer, use the IP route command to explicitly tell the router exactly where to send traffic for those distant destinations.
Now, when you're drawing this manual map, you've actually got a few really powerful options. You can create a network route, which points the way to entire subnets. That's basically like giving someone directions to a specific city. You can create a host route, which dictates a highly specific path for just one single IP address. Think of that like giving directions to one specific parking spot. Or you can set a default route. This is represented by 4 zeros, 0.0.0.0. Think of the default route as the ultimate all other destinations highway exit sign. If the router's map doesn't have a specific destination listed, it just funnels the packet right out the default route.
But wait, what happens if a router has two overlapping paths on its map? Like, let's say one route points to an entire corporate campus, and another route points specifically to the accounting department's server sitting inside that exact same campus. How does the router know which one to pick? Well, it relies on a golden rule called the longest prefix match. The router will absolutely always choose the most specific route available, meaning the match with the longest prefix length mask. It's actually incredibly logical. I mean, if you have general directions to a state, but highly specific directions to a house inside that state, you're obviously going to follow the precise directions, right?
Let's step into phase 3, routing inside the LAN.
Let's throw a little complication into the mix. What happens when we need to route traffic between different departments?
say HR and engineering, that are sitting in the exact same building, but they're logically separated into different virtual LANs, or VLANs. To navigate these local VLANs, we have to scale our map using some pretty clever techniques. One classic solution is what we call router on a stick, or ROAS. This is where a single physical router cable, the stick, uses virtual sub-interfaces to handle traffic from multiple VLANs all at once. Or, if we're talking about modern, super-fast networks, we use switch virtual interfaces, or SVIs. This actually allows a Layer 3 switch itself to perform the routing locally, so you don't even need a separate router.
Oh, but here is a massive, real-world trap, and it catches almost every new network engineer at least once. When you're setting up something like router on a stick, you are configuring two entirely separate physical devices, the router and the switch it connects to. Now, if you misconfigure the trunking on the switch side, the router has absolutely no way of knowing. None. Its interfaces will look perfectly fine, it'll think it's doing an amazing job, but the traffic will literally just drop dead the second it hits the switch. You always have to play detective on both ends of the wire.
Which brings us right to Phase 4, troubleshooting broken network routes.
And this is perfectly timed for the absolute climax of any engineer's day. You've built your map, everything was humming along smoothly, and then your phone rings. It's a frantic call from a user. The internet is completely down. Pure panic is setting in. As the engineer in the hot seat, where do you even begin? I mean, you've got hundreds of miles of fiber optics, dozens of routers, thousands of end devices. You need to isolate the exact problem, and you need to do it yesterday.
Now, what's really interesting here is how we use our diagnostic sonar. Most people already know about ping, and ping is great. It sends a quick echo request end-to-end, just to verify if a path is broken. But traceroute? Oh, traceroute is your precision scalpel. While ping just tells you, hey, a break exists somewhere out there in the void, traceroute actually shows you the exact IP address of the specific router where your packet died. It literally highlights the exact piece of the map that went missing.
So how exactly does traceroute pull off this magic? It does it by exploiting this brilliant little mechanism called time to live, or TTL. Think of TTL as a ticking clock attached to every single IPv4 packet to stop data from just endlessly looping around the internet forever. Every single time a packet hits a router, that router subtracts 1 from the TTL clock. If TTL hits 0, boom. The router kills the packet and sends an error message right back to the sender. Traceroute intentionally sends packets with a TTL of 1, then 2, then 3, literally forcing every single router along the path to sequentially run out of time, send back an error, and expose its exact location. It's genius.
Of course, it is absolutely vital to remember that when traceroute does isolate a dead end, the root cause isn't always some fancy software command. Seriously, sometimes a failed ping just means a physical wire got accidentally yanked out in a dense, chaotic server rack that honestly looks like a spaghetti monster. Effective troubleshooting means you have to investigate the physical, Layer 1 environment just as much as your logical routing map. I mean, a perfectly drawn map doesn't do you any good if the physical road is totally washed out.
Okay, the pressure is on, so here is your final bulletproof game plan. Step 1, run traceroute to isolate exactly where the dead end is. Step 2, securely log in via SSH to the very last router that actually responded to you. Step 3, check your map using the show IP route command. And hey, remember the golden rule of troubleshooting? Communication is a two-way street. You've got to check the forward path of the destination and verify that the remote router actually has a reverse path back to the sender. Fix the map, and the traffic flows again. It's a beautiful thing.
So, we've successfully unboxed our router, manually drawn out our static map, navigated our local VLANs, and troubleshooted a broken path like total pros. But here is a crazy thought to leave you with. Manually drawing maps with static routes? Yeah, that works perfectly fine for a single office building. But how in the world would you apply this exact same routing logic to a massive, self-updating global network with hundreds of thousands of paths that are changing every single second? Trust me, you could not type fast enough. That kind of scale requires dynamic routing protocols, and that is exactly the mystery we are going to unpack in our next explainer. Thanks so much for joining me on this deep dive. See you next time.